In this video, we're finding the volume of these three shapes and then comparing their volumes. So I think we should say that first of all, they all have the same radius, and the height of the cone is 6 centimeters, and so is it on the cylinder. And in fact, here they don't label it, but if the radius is 3, then that also means the diameter, anywhere I draw it, the diameter on the sphere is also 3 times 2, or 6, right? The diameter is double the radius. So the height also on the sphere is 6. Cone height is 6, right? From top to bottom. And the same thing with the cylinder. So let's, pause for a moment and make a prediction. If the height's equal in all of these and the radius is equal in all of these, which one will hold the most stuff? Which one will have the greatest volume? And then let's start working at the details. So to find the volume of the cylinder, I'm going to multiply, well, we'll use my formula, which is pi radius squared times height. Radius is 3, squared is 9, times 6 times pi, right? Simplify, we get 54 times pi, especially when you're comparing volumes here, right? This is 54 cubic centimeters times pi. Leave it in terms of pi. Keep your life simple. If you have to estimate it past that, go for it. But if you don't, leave it. Because here you'll start to see that to find the cone, basically, right, if we leave it in terms of pi, it becomes very easy to compare because the cone formula, 1/3 pi r squared times the height, plug it in, radius squared is 3 squared, or 9, times the height of 6, times pi, times a third. Well, 9 times 6 is 54, times a third, or divided by 3, right? What's 54 divided by 3? Well, it's 18, right? 18 pi. And that's less. It holds less than the cylinder. That makes sense. This cylinder, this cone will fit inside the cylinder, right? You can always just simply draw it. You can see it. The cone has the same height and radius. Right? There's all this empty space there, so the cone fits right in. And in fact, if you remember what the formula of a cone is, it's 1/3 of the volume of a cylinder with the same height and radius. So this volume over here is 1/3 of this, and we could predict that even without calculating because we know what the formula says. It says the cone is 1/3 of the cylinder, so right, it has to be 3 times less, and it is. 54 divided by 3 is 18. Now the sphere, using the same logic, this is where I think comes in handy. You could use 4/3 pi r cubed, but the volume of a sphere really, if we drew the cylinder around it, or we can picture the sphere fitting right in here, well, the sphere is just 2/3 of the cylinder with the same height and radius. So since they do have the same height and radius, we can just take 2/3 of our cylinder, right, of our cylinder's volume, and that will equal the sphere. So the cylinder's volume is 54 pi. Take 2/3 of that, and you've got the sphere. How do I do that? Well, take 54, divide it by 3. We already did that. That was the volume of the cone, 18. But here we're finding 2/3. So it's not 18 pi, it's 18 times 2, which is 36 pi. So the sphere there has a volume of 36 pi. It's kind of in the middle. And you can almost picture it. I'll try draw this one without messing it up. Use the circle tool. The sphere also fits inside, right, our cylinder here. Almost got it. Try. It's better. One more try. There we go. Okay. Now it's not a perfect drawing, but I think you can see that, or maybe you can't, but you can almost see, sorry if my drawing is throwing you off, that the sphere is going to fill more than the cone would inside the cylinder. And in fact, it fills 1/3 more of the cylinder than the cone does, because it fills 2/3 of the cylinder. So there's this nice connection between the sphere, cone, and cylinder that should not be forgotten, because it helps you predict how the volume changes between each shape. Thanks, I hope this helped.